Thank you, Jay. So welcome to this talk, which is going to be one of the fun ones and a little bit more applied than the other ones. So what we're doing is trying to turn shabby X509 certificates into elegant anonymous credentials with the magic of verifiable computation. And this is joint work with my colleagues Cedric, Marcouf, and Brian at Microsoft Research. So as you probably know, the X509 PKI, the public key infrastructure, is what is used for all kinds of client and server authentication purposes since it was created almost 30 years ago. So most well-known example is HTTPS, but if you look in the details of how it works, you have a set of root certificates that are part of your browser or your operating system, and there are the trust ensures, which are used for signing further certificates, which does delegation of trust. And ultimately, you have endpoint certificates that are issued to websites and users, and these are the ones that are used by application protocols for authentication. So if you look at the details of certificates, it's quite an old format, and it has a bunch of extensions that have been added over the years, mostly to deal with problems that happened quite early on with the system. So the main fields that you care about are the subject information and the public key, which is the core contents of the certificate. But you have a lot of extra information for restricting the purpose of the certificate, what is it meant to be used for, and extensions for checking whether it has not been revoked, and these kind of things. So if you look at how X509 authentication works in a typical setting, which is a little bit like HTTPS, so in the application protocol, you have an authentication challenge, and the person who owns the certificates is going to sign the challenge most often using the private key of his endpoint certificates, and it's going to send all certificates along with this signature for the person who does the verification to check. And it's quite common today to also use external evidence to make sure that this is actually a honest certificate chain. So typical examples are OCSP for revocation, and quite popular nowadays is variations of certificate transparencies, attack resilient PKI, and this kind of external evidence that are used to make sure that you're using a valid certificate chain. So all of the system depends on the certification authorities that are signing the root certificates, and they're doing their more or less what is the verification policy for the certificates boils down to what are the fields that are put by the certification authorities. So if we look at the problems with X509, you have several of them, but the one that we actually look at in this work, there are two aspects that we care about. So the first one is application heterogeneity, and it has been an important source of attack. So it's well known that you use the certificates for many purposes, including TLS, but SMIME also for image signature, wireless network authentication, code signing, document signing. And the consequence of that variety of application is that certificate verification libraries they have to implement, in addition to the basic validations, which are checking the signatures in the chain and some other very basic things, there's a bunch of application-specific checks that they have to implement, and this can be different across applications. So for TLS, you may be looking at hostname validation, which has some specific aspect, like if you have wildcard in names, you have extensions for having more names, and this is different, for instance, in SMIME, where you use email addresses. And the result of that is that if you look at the history of PKI failures, you see that there is an embarrassingly high number of problems that are due to misunderstanding of either the semantics of some of the security extensions. So one of the recurring problems you see is the basic constraints, which means that you can confuse endpoint certificates with CA certificate, and a lot of other issues related to the formatting and the ASN1 formatting of these certificates. So the other problem that we really care about, and we think is quite important, is privacy in X509 authentication. So this takes several forms. So the most obvious one is from the network perspective. If you see all of the certificates going on the network, then you learn not only the identity of the person who authenticates, but you also get a non-deniable proof that the person is authenticating in many cases. And the same problem applies for the external evidence that you're gathering, including OCSP and CT. So yeah, there have been some ways to avoid these issues, including the fact that some of this evidence is sometimes stapled, at least in some protocols, with a certificate chain, but it's not always available and it's not generic. So the other thing is that for these third-party services, you also learn some privacy-sensitive information when you are querying them. And the one that is the most difficult, but also maybe the most interesting, is that the person that you're sending your certificate to learns all of the contents of your certificate. And we think it's a problem because in many cases, you may have, in a high-trust PKIs, you can have very sensitive information that are stored in your certificates. So a typical example for that is there are many countries that are issuing ID cards and that contain X509 certificates that have your social security number and date of birth and this kind of information, and they're actually sent on the network when you are connecting to government websites. So the main idea of Cinderella is that we want to improve the cryptographic power of the PKI without changing the issuance practices. So we're not assuming any change from the point of view of the CAs, but we want to build a system that is privacy preserving using the same credentials as before. So the main idea works like that. So we have instead of having certificates validation code that is generic for all application, we start from certificate validation policy, which is something that is already specialized not only to some application like HTTP, but also to some set of issuers or class of issuers. So maybe a way of thinking about what this class could be is like extended validation you can treat as a class of issuers. So from that, we use a Gepetto compiler, which is generating two keys. One is used for evaluating computation, and so the evaluation key, and the other one is for verifying them. So after this initial setup phase, which is occurring only one time, we change the way that you're doing X509 authentication. So you still have an authentication challenge, but what is happening is that instead of sending your certificate chain to the peer, which is going to run locally the certificate validation policy, you're actually going to outsource the certification policy execution to the owner of the certificates. And this lets you control what kind of information you disclose from the certificate. So using the evaluation key, you can produce what is called an argument, a succinct argument of knowledge, or sometimes called SNARK, just call it proof. And this is in the cryptographic system, we're using always constant size, which is actually quite a big gain from compared to the evidence when it's sent on the network. So using the verification key, the person who is checking the certificate policy can actually make sure that the proof attests that the verification of the policy was done faithfully. So if we look in the cryptographic details of how this works, this relies on the Pinocchio scheme, which was presented 2 years ago. And the way it works is that it transforms programs that have two kinds of inputs. There are public inputs that are provided by the person doing the verification, and the private inputs are the ones that are kept private by the person who is doing the computation, and you have the zero-knowledge property over the private inputs. So you compile this program into an arithmetic circuit, and from this circuit, you generate the two evaluation and verification keys. So the important point is that this obviously is an advanced cryptographic techniques, and the more complex the program you're compiling, the larger the arithmetic circuit is going to be. So you have only two kinds of gates in this arithmetic circuit. You can only do addition and multiplication over 253 bits fields. And it's, as a result, it's a very difficult compilation problem if you want to have complex programs that are expressed into small and efficient arithmetic circuit that you can actually use. So the contribution of our papers are several folds. So we have a compiler from high-level validation policy templates to Pinocchio-optimized certificate validators. So this is already specialized. We do not compile a general-purpose certificate validation library. In fact, if we try to do that, it would not be practical. The circuit would be way too large. We also provide Pinocchio-optimized libraries for doing hashing and AES-N1 formatting, which is a binary format of certificates, and for checking RSA PKCS1 signatures. We also want to, so typically in the previous works on verified computation, the keyword is nearly practical, and we want to push this boundary to see whether we can actually have practical applications. So we actually built two exemplary applications on top of our contributions. One is TLS authentication, which includes revocation checking with a CSP, and we use actual certificate templates for that. And the other application that we present in the paper is an e-voting scheme that is built on top of Helios and that uses actual templates from Estonian ID cards. So the benefits of our approach are that the main selling point is that it's compatible with existing PKI and with existing credentials, not only at the format level, but also at the interface level, which means that if you have certificates stored on smart cards, you can actually use Cinderella for that. And it ensures uniform application of the validation policy, which is one of the controversial points that was brought up before at Oakland in the Frankenstein paper. So you ensure that everyone that uses the evaluation key is doing exactly the same evaluation checks. But at the same time, you have flexible issuance policies because you can use different Cinderella keys for different applications. So the anonymity aspect is that it lets you control exactly what are the fields of the certificate that you want to disclose to the person doing the verification. And minor, slightly controversial point is that you don't expose the actual contents of your certificate, which contain typically weaker keys cryptographically. So on the downside, what you have is a computationally expensive scheme, but only for the evaluation part, so the person who is authenticating. So I'm going to go back to that in the evaluation section. You also have a new setup phase, which is the one where you do the key generation for the evaluation and verification key, and it relies on the new cryptographic assumptions. So we have a soundness argument, which boils down to the fact that if you have successfully checked Cinderella proof using the verification keys, and it's equivalent to having actually ran the certificate validation program locally using the public and private inputs. So going into a little bit into the details, the way that we express high-level certificate validation policies is through the use of templates. So these are, in a sense, skeletons of certificates where you have some constant fields, and the ones that are interesting are the variable fields, so the one where you have variation inside the templates. And one of the core assumptions that we have to make for efficiency is that we have to have length boundaries for every variable fields, as well as variable lists of fields. So from these templates, we actually generate two outputs using a ad hoc compiler. So one is an untrusted native parser, and this is the one that is going to compute the private inputs that are used to help with evaluation. And we also provide generate the C verifier, which is the one that we send through the Pinocchio or Gepetto compiler to compile into the actual evaluation and verification keys. So if we look at the produced verifier here in the small fragments, you can see that the constants are going to be, so we rely on two main primitives, one for appending a byte and one for calling the reduction function. And we do unconditional appends for adding bytes and bounded loops for adding variable length inputs. So the next thing that I'm not going to go into the detail of is the verification of PKCS1 signature. So we implement a small arbitrary precision arithmetic library that uses the finite fields used by Pinocchio. And we actually verify RSA signatures using that. So I'm going to present only one of the two applications that I mentioned at the beginning. If you want to look into the e-voting one, please refer to the paper. So for our TLS clients, so we have switched the roles, so the client is authenticating to the server. We're going to generate the evaluation key and the verification key, but for efficiency, since as we'll see later, the evaluation is quite slow, we actually want to pre-compute offline a pseudonym certificate based on the real one that you want to use. And we do this operation by generating an ephemeral public key for the certificates and appending it to the proof using the X509 formatting. And we can actually transmit this proof and use the ephemeral key for signing the key exchange. And this lets you use Cinderella with no change to the TLS protocol. In terms of performance, the key aspects and the key point really is that the verification time is as fast, or even sometimes slightly faster than the native verification. So this is a logarithm scale, and the verification is taking about 8 milliseconds, which is comparable to native verification. Evaluation, as you can see, is typically several minutes, and similarly for key generation. So these are for single templates, but we also give you full application benchmark. So in this case, we look at complete applications, including TLS with 2 intermediates, which is quite a general application, and OCSP as well. So it actually checks for 5 signatures. And we get a very large number of multiplication in the circuit. In fact, I think it's one of the largest ever compiled, but still performance that is within 10 minutes. So in conclusion, this is one of the first practical applications of verifiable computing. And we enhance the privacy and integrity of X509 authentication without any change to the PKI and the certification authorities. And we actually provide prototypes for TLS and Helios. So this is the end of my talk. I will be willing to take questions.
Hi, Brian Ford, EPFL. This is really awesome work and a beautiful application of verifiable computing, I think. My question is, I'm a little concerned, in practice, if this became really practical, hopefully it will, the times will go down and stuff. I'm a little concerned about the implications on, say, PKI security and transparency. Mm-hmm. Like, say an attacker manages to secretly acquire or coerce some CA's private key somewhere, but now they only use it via, via this, and they don't have to basically disclose to anyone that they're actually using this path to manufacture any credential they want. Have you thought about this problem, and can you envision ways to address it?
Yes, of course. It's quite an obvious concern, and it's always a trade-off when you have privacy-enhancing technologies, is whether they actually let you have undetectable attacks. And in this case, so there are several aspects. So the one that is very important and non-controversial is the step where you generate the evaluation and verification keys, which is the CA bootstrapping of the system. So for this step, it is extremely important that it is done honestly, because it relies on a trapdoor value, which, if it is not honestly destroyed at the end of the key generation, lets you do universal impersonation without being detectable at all. So I think there are some answers. This is a classical problem in verifiable computation, and as a generally admitted answer to that is that you can actually distribute this key generation phase. So for this one, there is some answer. The other problem that you have is that you no longer have any visibility of the certificates that are used, and this seems to be in contradiction to the approach of ARPKI and certificate transparency. And for this other problem, we could argue that it's not completely contradictory in the sense that what you care about is not being identified on a given connection, but you are actually willing to put your certificate maybe in a very large database that someone is managing, someone trustworthy. And you can actually check a certificate transparency proof inside Cinderella and do that as part of the certificate validation policy. So this is actually possible to do.
Thanks.
Riyad Wabi, Stanford. So I'm wondering, how big is the proving key that the server needs to hold on to in order to generate these proofs?
Yes, excellent question. So in my evaluation, I only had time to present the timing aspect, but the memory aspect is quite significant as well. So the verification keys are quite small, a few kilobytes, so not larger than root certificates. But on the other hand, the evaluation keys are, at this point, up to 1 gigabyte large for the very complex policies. So yes, definitely there is a logistical problem of distributing evaluation keys.
Right, so does that mean that the web server needs, for each policy it wants to produce a proof for, needs one of these 1 gigabyte keys?
Yes.
Okay, thank you.